Assalamu alaikum, greetings, this is Dr. Bilal Wajid. So in the last lecture, in chapter number 3, we first introduced basic filters like low pass, band pass and high pass filters. And then in the next lecture, we discussed point processing, where our aim was to improve the contrast of the image. And now we're going to talk about mask processing. Now, mask processing is, it changes the image completely. I mean, you have a different individual before, and after they've put up the mask, it's a completely different individual after. So, in the mask, the important thing is, and this was discussed in the last lecture as well, this is point processing, where the original point is responsible for the output point exclusively. But in a mask processing, the input point and its neighbors, it could be 3 by 3, it could be 5 by 5, it could be 7 by 7. So in other words, that point and its neighbors are responsible for the output point. That's mask processing. So effectively, for instance, this is a 3 by 3. So what you really have is the output pixel x and y is related to the input pixel x and y. You have plus a and plus t here. In other words, plus a would be moving it right and left, plus b would be moving it up and down. So the number of it tells you it's a 3 by 3 or a 5 by 5 or a 7 by 7 mask. And then there's a weight associated with it. So there is a coefficient or a weight associated with each pixel. Okay, and the output pixel is just a linear combinations of the input pixels with some weights associated with them. So going back to the low pass, this is the simplest example, for instance, where the image, the pixel in question and its neighbors, all of them have the same weight, which is 1, and all you're doing is just taking the average. Now, when you take something like this and you pass it and you get the output image, effectively what really happens is you are smoothing it, but at the expense of getting rid of high frequency, it does attenuate high frequency components. It has therefore more of has a smoothing effect, but at the same time does cause some noise reduction, but it does blur the image a little bit. A somewhat better is this one. For instance, here obviously the pixel in question has the highest weightage as opposed to the neighbors. This is a better example. And the further you go away from the central pixel, the lower the values get. So the highest, or the central pixel or the central component has the highest weight, and the further you move away, the weight gets less and less and less. But again, this is more looks like an average. This is one example where you take the original image, and this is the passing it through a low pass filter. As you can see, it does smooth the image, but it has a blurring effect. The way you do this in MATLAB is you read the image. So you do that using image read function, and once you've read the image, you convert that RGB, so it could be a colored image, into its equivalent grayscale. So that's how you do that. And once you've done that, this is where you pass the filter. So notice back here, this is a matrix, 3 by 3 matrix. So how it's very easy to define a matrix. You just say 1, 1, 1, colon. So that's the first row, 1, 1, 1, colon, 1, 1, 1. And you open and close it with a square bracket, and you multiply with 1 by 9. And this is exactly what you've done here. If this would have been, if you wanted to initialize this, you would open up the bracket and you would say 1, 2, 1, colon, 2, 4, 2, colon, semicolon, 1 comma 2 comma 1, and then you're going to close the bracket. So all the rows are differentiated with semicolons, and the columns are differentiated with commas. So, and then you would multiply by that 1 by 16. So this is how you define a 3 by 3 masked filter. And if you want to apply this filter to this image, all you do is you apply this function, which is image filter, where you provide the image first and then the filter, and then you're showing the original image. This is stored as smooth image, and then you're showing the filtered image. Now, what we've really done is take the mean here. If you've noticed, this was technically the mean. This is again a mean with some weights, but there is something called a median filter as well. And a median filter, what you do is you just find the median value. So you have all these pixels, you put them in increasing order, and you take the median. So the difference between mean and median is, as a revision, if you have one list, the mean is the sum of them all divided by the number of elements, so that's 4. If you take the same list and you order it in increasing order, and then you take the middle value, that's the median. Now here you don't see the difference, but you will see the difference here. So here I have another list. As you can see here, there is an outlier here, which is 99. So in this particular list, 99 is the outlier. So again, if I take them, sum them all up, take the average, I get a much larger mean. So the outlier basically puts a lot of weight in the list and moves the mean significantly. Imagine there could be a number like 1000 here, not 99, 1000. In that case, that number is just shifting the average completely. So means are affected by outliers. At the same time, if we take the same list, we order it in increasing order and take the middle value, well, the median is not affected at all. So median in one way is not affected by outliers. So going back to the median filter, the whole point is you take the image and its nearest components, you order them in increasing order and take the middle value. That's the median filter. The biggest advantage is, it does smooth it, but it does avoid the blurring effects associated with the linear smoothing filter. As an example, this is your noisy image. It's done the same way. So you read the image, you take the gray values, you introduce salt and pepper noise. This is the salt and pepper noise. You can see that it's black and white. So this is your salt, this is your pepper. So you introduce that with image noise, where you take the original image and you mention what kind of noise you want to put in, and then you pass it through a medium filter, and you're kind of like storing it to a different image, and then you show the original image with the noise and the medium filter. Notice the noise reduction has been done, and there is not a lot of, it doesn't have that bad blurring, the same that we saw with the low pass filter. This is much better. As an example, if you want to look at comparison step by step, this is the original image. Here you have introduced the salt and pepper noise. This is the low pass filter. Again, the noise hasn't been removed that well either. And the other thing is, it's a little blurry. It's a little blurry as well compared to this. This, however, is a significantly better image. The noise has been completely reduced. The high frequency components have been reduced. So it doesn't look like jumpy, but it provides a smooth transition. This is a much better filter. Now the other aspect is when you don't want to blur the image, rather you want to enhance some blurred effects or to provide sharper images. Those are called sharpening filters, and they're called high pass and high boost filters. Again, high frequency components are the ones where there there are edges, because suddenly the gray level changes significantly, and that's why you see an edge. Low pass components are, regions within the texture itself, within the tissue itself. So these, for instance, are your high frequency components, and all of the other regions are low frequency. So what really high pass filter does, this is an example of a high pass filter. Now a high pass mask, which looks like this, has the central component which is a positive coefficient, and the outer components have a negative coefficient. Now this is typical for a high pass filter. The values can change, but the central pixel has a positive coefficient, the weight is a positive number, whereas the surrounding pixels, their weight has a negative coefficient. So this is an example of a high pass filter. Now when I pass this image into a high pass filter, the results are not very nice, but it does show you the impact. What really has happened is that the high pass filter has eliminated most of the low frequency components, which are in fact in this case necessary for an improved image. They were actually needed. So it was necessary to sharpen the textures, but when you remove the low frequency components which are necessary, there's not a lot of help that you're going to get. So another solution is to use a high boost filter. Now a high boost filter is a combination of a all pass filter and a high pass filter. So this was your high pass filter that we just saw right now. The central component has a positive coefficient and the neighboring components have negative coefficients, and you take the average of all of them. That's what you're doing. Divided by 9 is basically adding it all up and averaging it. This is a all pass filter, and technically what you're doing is you're not changing anything. This is more like a point transformation if you really look at it, because only this pixel in question is responsible for the output. All other neighbors are all 0. So this is more like a point to point transformation, where you're just adding it with a minus 1, which could be your a weight. So this is your all pass filter because it passes everything. It really passes everything. It doesn't attenuate anything. And when you combine this an all pass with a high pass filter, you get a high boost filter. And again, notice here it's just if you add them all up, 0 minus 1 is minus 1, and 1 with an 8, this is a minus 1 plus 8 over 9, there's a weight associated with it. This is a high boost filter. Now high boost filter does pass the good high frequency components, but it does retain some sense of it's better than a high pass filter. But the important thing is this value A. This value A is usually found by trial and error. Okay? It's usually found by trial and error. So this filter, high boost filter, does give better results than a high pass filter, but the value A has to be determined through trial and error. The last one is called derivative filters. Now in some sense, if you look back over here, what you're really doing in a low pass, you were taking the average, which was more like the summation. What you're doing is summation. So summation retains low frequency components. So, and summation is more like integration. So the alternate of that is differentiation. So if integration allows low frequency components, maybe differentiation allows high frequency components. So that's the idea behind derivative filters. Now derivative filters are again kind of like high pass filters, but here, because we're talking about images which are two-dimensional in nature, so your derivative has to be both in terms of x and y domain. A good approximation is this. Now, because we are not dealing with continuous numbers, we're dealing with pixels, and these pixels have values. You know, in some sense, a derivative would look more like a difference. So this is a Robert-Cross gradient operator, or a Robert-Cross gradient approximation of a derivative filter, where this is your central pixel. So it's Zn minus Z5 and Z8 minus Z5. Now these are derivative filters. Again, they are not very forgiving to low frequency components, and we've seen that here. A lot of the low frequency components may actually be necessary to see the background. You want to sharpen some edges, that's fine, but you want to have some sense of background and not remove everything. So they usually combine with some low pass components to improve better images, to improve the image quality. So this lecture we talked about, that was the end of mask filters. We talked about up till now, we've talked about what's an ideal low pass, ideal high pass. We talked about band pass, ideal filters. Now we've also talked about all pass. We also talked about Butterworth filters up till now. And then we moved towards point processing and mask processing, which was space domain filtering. So both point processing and mask processing were present within the area of space domain filtering. Now we're moving towards, in the next lecture, inshallah, we'll talk about frequency domain filtering. And up till that time, thank you very much. Assalamu alaikum.